This lesson is going to introduce us to Standard 8b, which is graphing rational expressions, including asymptotes and removable discontinuities. What we want to understand is that a rational expression is a fraction with polynomials in it. So when we're graphing rational expressions, we want to represent on the graph that the factors of the denominator cannot equal 0. So when they can't equal 0, we got to represent that in different ways. So one way is called a vertical asymptote. Another way is called a removable discontinuity. What a vertical asymptote will look like is it'll look like a dotted line that we'll get close to but not actually get to. And then a removable discontinuity will look like an open dot on the graph that the graph actually kind of skips over at that spot. So let's start with the vertical asymptotes. Usually we represent that with the dotted line on the graph, and then the graph itself, which we get from the graphing calculator, will then go off to infinity in one direction or the other close to that asymptote. So it represents something that we get too close to but don't actually graph. These occur when the denominator factor when we factor the denominators, when that denominator factor does not cancel. If it doesn't cancel with something in the numerator, then it results in drawing one of these asymptotes that are dotted lines. So that's important to remember. Now when we move to the removable discontinuities, those removable discontinuities, when we draw the graph, look like holes in the graph. And so when we draw these, you're going to see graphs that are very familiar, but when you draw them, you'll end up having what looks like a hole where the graph actually skips over it. So when we draw this one, what it will look like is, let's say we draw something that looks like a parabola. Then we get to the spot where the removable discontinuity happens and we draw a hole in the graph because it skips over that spot. So you'll see these, what they look like are holes in the graph or open dots. We could call them either one in the graph. These occur when you factor the numerator and denominator, and when that denominator factor that you have does not cancel. That results in on the graph having an open dot on the graph. So when the factor does, in this case, when the factor does cancel, it results in the removable discontinuity. When it does not cancel, we have an asymptote. When it does cancel, we get that hole in the graph or where we skip over a spot in the graph. So here are some steps for doing this. First step is to factor. You want to factor the numerator and the denominator, and then you see if there are any common factors in the numerator and denominator that you can cancel. Once you see which ones cancel and which ones don't, we then know how to draw the vertical asymptotes and the open dots on the graph. What we do is we separate that into two groupings. After we look at the factorization, what cancels and what doesn't, if we have denominator factors that cancel, that results in open dots. If we have the denominator factors that do not cancel, we get vertical asymptotes. So let's make sure we enumerate that. So the first part is look for the denominator, and if you have canceled factors, then you have open dots. Okay, so that what says there is open dots when it does cancel. Okay, I'll scroll up in just a second for you, just so you can see that. Part B is when the denominator factors, let's scroll a little bit. So part B is when the denominator factors do cancel. Okay, we had the open dot, but when the denominator factors do not cancel, we get an asymptote we draw that vertical asymptote, that vertical dotted line on the graph. Those asymptotes are, again, lines that we get close to, but we don't actually get to as part of it. Okay, we approach them. Let's do some examples. In this first one, it's already factored. It's already in a form that we can use. Fourth step is once you do that, then you do look to your graphing calculator. That will give you what the shapes are around those asymptotes and those open dots. So once you know where the open dots and the asymptotes are, use the graphing calculator to determine what the shape of the rest of the graph looks like. You can use your table and also the screen to help determine that. Okay, so for this first one here, we know that we're going to have a vertical asymptote at x equals 3 because that denominator factor does not cancel, so that results in an asymptote. So what we do is we draw a dotted line then at x equals 3. And then we look at our graphing calculator to see what the shape is. And what we can see on the graphing calculator is we've got on the left part of the asymptote, we've got a graph that starts near the axis and then goes down to negative infinity. And then it goes the other side of the axis, it starts at positive infinity, in the direction of positive infinity, and goes toward the axis. All right, now let's try the next one. Let's see how this one works for us. Notice that, again, we have denominator factors that do not cancel. So those become vertical asymptotes. You're going to have the vertical asymptote at x equals negative 4. And then also at x equals 2. Now that's going to make it interesting because now we're going to have to go on both sides of those asymptotes and in between them to see what we get for a graph. Okay. So I'm going to draw those asymptotes, then we'll scroll up a little bit to see the graph. So asymptotes at negative 4 and at 2. On the left side of this asymptote, the graph starts near the axis and then goes up toward infinity. And in between the asymptotes, which I'll scroll up, you'll be able to see it's down below the x-axis and then looks kind of like a parabola, but it's on the other side. And then we have one on the right side of the axis of the asymptotes that looks like the one on the left, just a mirror image. Okay, so that's what our graph looks like when we have two asymptotes. All right, let's look at the next one. This one requires a little bit of factoring because it's not factored yet. So let's go ahead and factor the numerator. The factoring of the numerator gives us x plus 3 and x minus 1. And on the denominator, we already have an x minus 1, so we can cancel out those x minus 1 factors. That leaves us with just x plus 3, which we know looks like a linear equation. It looks like a line. So since the x minus 1 in the denominator canceled, we have an open dot at x equals 1. So we'll draw that line of x plus 3, and when we get to x equals 1, we'll stop. We'll then draw an open dot there, and then we'll continue after we skip over it. There's our open dot at x equals 1, and we just keep continuing the line on both sides. I'm going to do something similar on our last example here. Our last example, if we factor that denominator, the denominator again factors into that x plus 3 and x minus 1. And since this is the reciprocal of the other one, it has a different effect on what's happening, because now that we've got those x minus 1s that can cancel, we end up with just 1 over x plus 3. And that canceled factor of x minus 1, that becomes an open dot, whereas the one that doesn't cancel, the x plus 3, which gives us x equals -3, is a vertical asymptote. So the one that doesn't cancel, vertical asymptote. The open dot at the one that does cancel, x equals 1. So when we draw our graph, we'll make sure we start with the vertical asymptote. So at x equals -3, we'll draw that vertical asymptote. Then we go ahead and look at our graphing calculator to see what this graph looks like. And to the left of the asymptote, again it starts near the axis and then accelerates down to -infinity. To the right of the asymptote, it starts as it approaches infinity, and then we got to stop the graph as we get to 1. So get to 1, we draw that open dot, and then we keep going, getting close to the x-axis. So there you have it when it both cancels and doesn't cancel for vertical asymptotes and open dots.